Is everything good to go, Ivan? I'm going to assume that everything's good to go. Can you guys give me a thumbs up? I can kind of see you guys. Perfect. Thank you. Great t-shirt. I appreciate that. So let's get rolling. I can see that our numbers are dwindling here. I am getting a lot of emails about students who are sick. Obviously, there's a lot of things going around. And as I mentioned before, your health should be your number one priority. So if you aren't feeling well, oh, hold on. Can you not hear me? Let's see. Ivan, can you say something into the computer? So you guys appear to be frozen on my side. I'm gonna give it a second. Oh. Okay, if you're joining us from the live stream, I think they have to log back in. So we'll start again in a minute. So just hang tight and hopefully you're all feeling all right at home. Okay, I can see you guys, but I don't know if you can hear me or not. Ivan, can you unmute the computer and just tell me if the audio is okay? Okay, so it sounds like you guys can hear me. So hopefully you can, and we'll just get rolling from here. So as I was saying, I'm getting a lot of emails about sick students. Your health, it should be your number one priority. If you aren't feeling well, please, please, please don't worry so much about this class. I will do everything I can to work with you through this. I am live streaming this every day that we teach, and then there are asynchronous videos. So you can watch it in real time at home or at a later time if you aren't feeling well. So please take care of yourself. Remember to drink a lot of fluids and get a lot of rest when you aren't feeling well so your body can fight whatever it is you may have. So I want to spend a minute real quick to talk about our upcoming chapter quiz. So as you know, each chapter we cover is going to have a chapter quiz, and our first chapter quiz is on Monday. So on Monday, it's going to be a quiz that covers everything we talked about from chapter 1. So in the structure of the quiz, there'll be 10 questions. They're all going to be multiple choice, just like the mini quizzes. And you will have 1 hour once you log in to take it. Now, you can log in anytime from 12:01 a.m., so basically Sunday night at midnight, until 11:59 p.m. on Monday night. So there's a 24-hour period that you can take your quiz, but you just need to have 1 hour to set aside to do it. Okay, so the best way to prepare for this mini quiz, as I mentioned before, or for the chapter quiz, is to look at your mini quizzes. If you go into your gradebook in Moodle, you can click on them and review which ones you got right and wrong. Make sure you understand what is going on with those. And then also check out your homework and make sure that your notes are really organized, okay? So one change that we're gonna be making moving forward to the mini quizzes is that starting in chapter 2, so starting with the limits and continuity quiz, you are gonna have 2 attempts on each mini quiz. And so with that, there also is an enforced 1 hour wait period between attempts. So you can't take an attempt and then immediately take another attempt, okay? So we wanted to do this to give you an opportunity to start to think about your learning and what you know and what you don't know. So what's gonna happen is you'll take your first attempt and you'll think about what parts of it you felt really confident about and what you need to review, what you felt like you weren't sure about. Then you'll use that hour to go ahead and review your notes, and then you'll take a second attempt, and your highest attempt is the one that will be recorded. So there's no penalty in taking the second attempt. So if you get a 3 on the first attempt and you get a 0 on the second attempt, it takes the highest grade. However, you will not know your grade from the first attempt until the whole thing is closed. So what you want to do is you want to take this mini quiz twice, because 1, it's going to give you exposure to more problems to help you prepare for the chapter quizzes. And 2, there's no penalty to take the second attempt. Again, the only sort of thing you need to remember is that there's an enforced 1 hour waiting period. So if you don't take your first attempt at the mini quiz until 30 minutes before the deadline, you won't get to take the second attempt. And you don't have to take the second attempt, but it is a good idea, okay? So you'll have 2 attempts moving forward on the mini quizzes, not the chapter quiz, just the mini quizzes, to help you with your learning and understanding, okay? So that'll start with this limit and continuity quiz that's due on Sunday. So if you've already taken an attempt at the quiz, most of you have not, because that's what we're covering today, but you will have 2 attempts. So you could take an attempt tonight to feel it out and then do another attempt on Sunday morning, something like that. It doesn't have to be 1 hour later. It has to be at least 1 hour later. Okay. I think that's it in terms of regular announcements. Drop-in help, you know, today, tomorrow, Sunday. So if you have any questions that you have preparing for the chapter quiz, make sure you stop in there. There is another sine cosine review tonight with William. The links are in the email I sent you and also posted on Moodle. And yeah, so we'll just keep going forward from here. So today we're going to talk about limits and continuity. And this is just sort of a conceptual topic that helps lead us into chapter 2. And so we're really going to be thinking about this idea of closeness. If you have taken a form of calculus before, we are not going to be going nearly as in depth as most more formal calculus theory-based courses go, because we want to get to the applications. Okay, so I'm going to go over to the dot cam. Whoop. Oh, I forgot my marker. Hold on 1 second. I'm back. Okay, so limits and continuity. So we want to talk about what is a limit and what does it mean for a function to be continuous. These are 2 different topics that are related. We're not going to go a whole lot into the relationship between them, but there is sort of 2 distinct topics that we're going to be talking about. So we're going to talk about limits first. So when we say that we are taking a limit, what the limit is the limit is the dependent value, so the y value that a function approaches, so what number are we getting close to, as the independent variable, so along the horizontal axis, approaches some value c. So the idea that we should be thinking about is as x gets close to this number, then what does y get close to, right? That's what we're doing. So the notation for this, when we talk about limits, looks like this. So the limit as x approaches c of f of x equals L. And what that means is we're going to let x get close to some number, and we want to use that to figure out what y gets close to. Okay, so we're going to look at this in sort of a picture form to try to understand what this means conceptually. So let's consider the case where c equals 2. Okay, so if we take the limit as x approaches 2 of our function, that means that we are trying to get close to the number 2, right? So we think about our function, and notice I'm drawing these arrows. I'll talk about this in a second. So as we get closer and closer to 2, then our y values are getting closer and closer to 4, okay? Now, you may be looking at this and thinking, well, f of 2 equals 4, right? We know the functional value. Now, when we talk about limits, we never actually plug the value in. We talk about what happens as we get close to that number, and that may feel really silly right now to you because this example is pretty straightforward and we can see what the y value is. But the benefit of doing this is when we have functions that are more complicated, we can figure out things about them where this functional value doesn't exist. So if there was like a hole or a weird jump, we still can find the limit. So one thing that's important about limits is that we don't just plug the value in, and we'll see some examples of how that wouldn't work anyway in a few minutes. But conceptually, I want to make sure we have this idea of closeness down. We get close to 2 in the x direction, which leads us to getting close to 4 in the y direction. So I want you to notice that when I talk about getting close, I put arrows on both sides, and we're going to learn in a few minutes about the notation of this. But when we approach a value, we have to look at it from both sides, right? So how are we approaching it from the left? How are we approaching it from the right? And do they then approach the same thing in the y direction? Okay, so here the answer is yes. Everything, is approaching 4 in the y direction. So that's what limits look like visually. Okay, and again, we want to do this for functions that may or may not behave exactly how we think they will. So let's look at an example of sort of, I'm going to say a misbehaving function, but it's not really misbehaving. So here, right, think about the function x squared minus x minus 2 over x minus 2, right? Let's pretend for a minute that I didn't have my picture here. And I asked you to find the limit as x approaches 2 of this function, right, of f of x. If we tried to plug a 2 in, right, we would run into trouble because you can't plug a 2 into the denominator, right? You get 0. Turns out if you plug a 2 into the numerator, you also get a 0. You end up with 0 over 0. So that's what I was trying to say before, where we don't want to just plug a value in. We want to understand what's happening sort of as we get close to 2. So here, as we get close to 2 from the left and the right, we can see that my y value is getting close to 3, okay? So even though we can't plug 2 in, the limit still exists. The limit is still 3 because we never actually plug in 2, we just get close to 2. So when we approach 2 from one side or the other side, the y values are approaching 3. So again, these pictures are all meant to give you this sort of conceptual idea of what's happening. And so now we want to formalize this a little bit more algebraically because we don't always have the picture to look at. Okay, so first we want to break this down and talk about this idea of getting close to 2 from the left and from the right, right? So we're getting close to 2 from both sides, and that's going to be important in our work. So we're going to start by talking about some notation here. I'll write it a little bit bigger. I know you can't see that as well. So in order for the limit to exist, okay, the limit from the left has to be the same as the limit from the right. They both have to be approaching that same value. Like in the last example, it was approaching the value of 3. So when we talk about approaching the limit from the left, we're going to use notation that's different when we talk about using the notation of limit from the right. So I'm going to just write this a little bit bigger in case you can't see it. This is the right. And this is the left. Okay. So when we talk about approaching the limit from the right, we use this little plus notation to indicate that we are coming from values a little bit bigger than the right. This is specific to x going to 0, but it's this notation here, this little plus sign, that tells you that we're coming from the right. And it's the minus sign that tells you that we're coming from the left. So we're going to be making sure that we are approaching the same thing from the left and the right. If we are approaching the same value from the left and the right, then we can just use the limit in general. And we'll see what this means with an example. Okay, so let's do an example together of what this is going to look like. Focus that. Okay, so we have the limit as x approaches 3 of 9 plus x. Okay, and so what that means is we're letting x get close to 3, and we want to figure out what the y value is going to be on the function 9 plus x. Okay, so there are no holes or weird things happening with this function, but it's a good way for us to practice on something that's relatively straightforward. So again, we need to check from the left and the right, and we're talking about closeness. So these are the two things we really want to develop in this particular example so that we can get used to this. So when we think about approaching a number from the left or the right, you really want to think about like a number line, right? So here we're approaching 3. So we're thinking about what are values slightly to the left of 3, which means slightly smaller. So that's where we get 2.9, 2.99, 2.999. So we don't want to use values like 1 and 2. Those aren't close enough. We want things within 1/10, 1/100th, 1/1000th. So this here, this is our left-hand approach. So we plug in values that are really close to 3 on the left. So when you plug in 2.9 into 9 plus x, we're going to get 11.9. Then we get 11.99, and then 11.999. Okay, so we also want to do this from the right. And when we do this from the right, we're going to be using values that are slightly bigger than 3 to get close to 3. And so those types of values are things like 3.1, 3.01, 3.001. So when we plug those in, we get 12.1, 12.01, 12.001 from the right. And so this is where we put on our mathematician hat and we say, what are we approaching, right? Because we're never going to get the exact value since we're not allowed to plug 3 in. Well, here, 11.9, 11.99, 11.999, that's approaching 12, right? Every time you add a 9, we get a little bit closer to 12. Same thing over here, 12.1, 12.01, 12.001. We're adding a 0 every time. So this is approaching 12. So what does that mean? That means the limit as x approaches 3 from the left, we use that minus sign, of 9 plus x equals 12. And the limit as x approaches 3 from the right, we use that little plus sign of 9 plus x equals 12. So those are the same. As long as they are the same, then we can say the limit as x approaches 3 of 9 plus x equals 12. Okay, if they are the same from the left and the right, that means that the limit exists. If one of them was different, we would say that the limit as x approaches 3 does not exist. It would only exist from the left or the right, but not in general. Okay, so this is the approach we're taking. So we're going to be plugging numbers into different functions to see what's happening. So I wanted you to try one of these that I think is a little less clear what the answer is going to be. So here, I'll write the function just a little bit bigger in case you can't see it. But we have the natural log of 2 plus x minus the natural log of 2, all divided by x. So that's the function we're talking about. And we're taking the limit as x approaches 0. So we see that we can't just plug in 0 because we'd have a 0 down here and a 0 on top. So instead, we have to get close to 0 and see what's going on. So you're going to try to do this from the right. So numbers that are bigger than 0, but getting close to 0. You're going to try it on the left with numbers that are getting close to 0, but are a little bit less than 0. So what I want you to do is take about 2-3 minutes, plug these in very carefully, make sure you're using parentheses, and see what these values are and see what they are approaching. Okay, so you'll do it from the right, you'll do it from the left. If they approach the same thing, then you can say that that's what the limit is. Okay, so try to plug those in. Again, I'll give you 2-3 minutes. Feel free to check in with someone next to you and just be really careful with your parentheses when you plug things in. All right, take about 30 more seconds to finish up whatever part you're working on. All right. So as we plug these values in, we sort of look at what's happening to try to figure out what we're approaching. So we started with 0.48 and then 0.49 and then 0.4999. So this is approaching 0.5. Again, we are using our mathematician hat to say, okay, we're pretty confident that this is where this is going. And so again, the way these numbers got chosen was that I was getting close to 0. These are the values I would pick to be close to 0 from the right. From the left, when I plug things in, I see I have a 0.51, 0.50, 0.500. So these are adding more zeros, which again is leading this to approach 0.5. Okay, so since the limit from the right is the same as the limit from the left, okay, that means that the general limit also is just 0.5. That means it's approaching the same thing from the left and the right. Okay, so this is how we approach limits. The thing you just really need to be careful about is whatever number you're approaching, typically you end up with like a 0.99. Like when we were approaching 3, we did 2.999 and 3.001. 0 is sort of the special case where you're going to have positive and negative numbers near 0. So that looks a little bit different than the other integers. Okay, so far we've looked at cases where the limits from the left are the same as the limits from the right. And typically, if you are working things out algebraically, that's going to be true. But there are cases where it's not true, right? Where the limit from the left is different from the limit from the right. So we're going to look at an example where that happens. Okay, so here we have, what are you doing? There we go. Consider the graph below, and we want to use it to determine if the following limits exist, right? So we're trying to figure out what these limits are. So we're considering what happens as the limit as x approaches 1, the limit as x approaches -1, and the limit as x approaches 2. So for each of these 3 limits, we need to write down the limit as x approaches 1 from the left, what that is, the limit as x approaches 1 from the right, what that is, and then if they are the same, then we can fill in the value, and if they are not the same, we say the limit does not exist. So I want you to try this. I want you to write down what you think the limit is from the left and the right for each of these 3 limits, and then based on this graph, and then we'll go through it together. So I'll give you about 2 minutes. See what you can figure out. Feel free to check in with someone next to you, and then we'll go through it together. right, take about 30 more seconds. All right, so we'll just do these in order. So the first one is the limit as x approaches 1. So when we approach 1 from the left, we are starting at values smaller than 1, which means we are on this part of the function here, right? And so as we get closer and closer to 1, the y value gets closer and closer to 1. So the limit, oh, that one was from the left. The limit as x approaches 1 from the left is 1. However, when we approach 1 from the right, okay, we're picking values that are slightly bigger than 1. So that means we're on this function up here, okay? So as we get closer and closer to 1, remember we never equal 1. So that means that the y value is approaching 3 as we approach from the right. Okay, so again, we're on this function because we're values slightly bigger than 1. So since these are not the same, right? From the left, we were approaching 1. From the right, we're approaching 3. Then we say that this limit does not exist. We often notate that with DNE. It's not the same. So the limit from the right exists. The limit from the left exists. We have those values, but the limit in general does not exist. So let's look at the next one. So we're going to look at -1. So the limit as x approaches -1 from the right. So -1 is over here. So when we approach from the right, we're slightly bigger. So we're going up here. And we see that that's approaching 1. And when we approach from the left, we're still on this function, but now we're coming down towards 1, but that's also approaching 1. So the limit as x approaches -1 from the left is also 1. So those are the same, okay? If they are the same, that means that the limit as x approaches -1 is that value, which we found to be 1. They're approaching that same y value, okay? So finally, let's look at the limit as x approaches 2, just underneath a little bit. So the limit as x approaches 2 from the right, so 2 is here. When we approach from the right, we're approaching from values that are slightly bigger. So we're coming down here to see what the y value we're approaching is, which is 2. And when we approach from the left, okay, we're back on this guy up here, but now we're coming the other way, right? So we're approaching here from the left to get close to 2. And so that y value is 3. So again, those are different, 2 and 3. So the general limit does not exist. So that's how we look at that on a picture, and that's what it would look like if it does not exist. You just have something different on the left and the right. And so we just have to be careful to make sure that we're using the notation and doing what we're asked. So if you are asked on a homework problem to find the limit from the left, you can't report the limit from the right because it may be different, right? So make sure you're just looking for that notation, whether it's left or right or in general, okay? One other thing that comes up for us sometimes is when we are looking for a particular limit, sometimes it makes sense to simplify the function before we take the limit. So I'm going to write this bigger because it's pretty small. So we have the limit as h goes to 0 of 2 plus h squared minus 4 divided by h. Okay, so notice again, we can't just plug in our 0 for h because we get 0 over 0. Now, we could do a table at this point, okay, and we would get the right answer, no problem. But sometimes you're instructed to use algebra first, and that means that it's going to simplify in a pretty nice way to make it a little bit easier. So I'm going to have you try this, and this is what I want you to do. I want you to FOIL this out, cancel and combine any like terms, and see if you can simplify any further. And then you are going to do a table that has values towards 0 from the left and a table as we approach 0 from the right. And we're going to see if they're the same. And if it is, then we'll know what it's approaching. Okay, so we're going to do some algebra first. So try it out, right? So FOIL, simplify, and then do the tables. So I'm going to give you about 3 minutes because there's sort of a lot of steps there. Feel free to work with someone next to you. If there's TAs there, they'll come around to answer your questions, and then we'll go through it together. right, take about 30 more seconds to finish up wherever you are. All right, so let's walk through this. So again, you could certainly just start with a table, but sometimes, depending on how strong your algebra is, it's just easier to simplify first and then go ahead and approach from the left and the right. It's really a matter of preference, but I just want you to know your options here, okay? So if we were to FOIL this out, we would get 4 plus 4h plus h squared. So again, I did, 2 plus h times 2 plus h. So the 2 times 2 gives me 4. The h times h gives me h squared. And then we have a 2h plus another 2h. So that's where that came from. I FOILed. And then I have my minus 4 over h. What I notice when I try to combine like terms is that the 4 and the minus 4, they're going to cancel out. So that leaves me with 4h plus h squared over h. What I notice here is that everything has an h in it. So I factored the h out on the top part. So 4h plus h squared, I pulled out an h. So I have h times 4 plus h over h. The benefit here is that if it's factored out, I can then cancel it. So that just leaves me with the limit as h goes to 0 of 4 plus h. So it's easier to plug things into this than this. That's why we might want to simplify first. Again, it's really a matter of preference. Some people are really strong with their algebra, and this would only take them, a few seconds. If this was giving you a lot of trouble and you don't particularly like the factoring and the things of that sort, you can still just use the table on the original function. You just have to be careful with parentheses. So now we have the limit as h goes to 0 of 4 plus h. So we are going to look at what happens as we get close to 0 from the left and the right. So when I do it from the right, I'm picking values really close to 0 that are a little bit bigger. So 0.1, 0.01, 0.001. So I get 4.1, 4.01, 4.001. So those numbers are certainly approaching 4. And again, that was from the right. So the limit as h goes to 0 from the right of my function. And then when I do it on the left, right, I get 3.9, 3.99, 3.999, right? So again, that's also approaching 4. So the limit as h approaches 0 from the left, right? So these values are a little bit smaller of my function is also 4. So since they are the same, then my limit that I started with has to be 4. So even if you simplify it, as long as you're careful with your algebra, the limit maintains the same dignity, right? So the limit is 4. So that's another approach you can take with limits. If you see a way to algebraically simplify, you can do that first. Again, you don't have to, but sometimes it's helpful, okay? So the last sort of limits example that we're going to talk about, we want to just sort of use all of this intuition and all the things we just talked about to look at this graph. And I want you to think about it and think about which points on this graph do you think that the limit does not exist? Okay, so I want you to look at it. I'm going to give you 1 minute to sort of jot down where you think the limit will not exist using everything we just talked about. You don't have to calculate things out. You can just say, it doesn't exist at, maybe you're guessing 3.5 for some reason, but just write down where you think that limit would not exist. I'll give you 1 minute to look and then jot down your thoughts. All right. So hopefully when you look at this graph, the places that you are thinking about are the places where the function changes, because that's where it's going to be different from the left and the right. So that happens here at -1. We can see the limit from the left is coming down towards 0, and the limit from the right is going to be at 1. So at x equals -1, that's one place where the limit does not exist. And then similarly, at +1, we also have this sort of change in function, so that the limit from the left is 1, and the limit from the right is 2. So those are different. So the limit also does not exist at 1. So visually, you're looking for like breaks and jumps and things on a graph to figure out where the limit doesn't exist. If there's no breaks or anything, then we can see, if we were taking the limit at 3, it's going to be the same from the left and the right, right? It's going to be approaching that same y value, okay? So you should be able to look at a graph and just have a general sense of where the limit does and does not exist based on where it changes, okay? So that's sort of the end of the limits part, and we're going to jump into continuity. These are related, and I do want to point out that if you've learned about continuity before, there's sort of the straightforward version of continuity and the more complicated definition version of continuity. We are going for the more straightforward version of continuity because we just need to know how continuity works as a concept and not prove the back end of why it works, right? Because in this class, we really want to get to the applications and we do less of the theory. So you may know a little bit more about continuity than what we're going to talk about, and that's okay, okay? So the continuity of a function, we use the word continuity or continuous to describe a function. And a function is said to be continuous if there's no breaks, jumps, or holes on the interval being considered, okay? And so typically, when this is first introduced, you hear things like, if you can draw the function without picking up your pencil from the paper, then it's continuous, right? That's a good sort of way to think about it. And so the technical definition, which we're not going to get into the background of, but we're going to just say what it is here, is that we say a function is continuous if the limit as we approach a value is the same as the functional value, okay? And so all that means is if we were to take the limit from the left and the right, we would get the same thing as if we just plugged the value in, right? That's what it means to be continuous, because that's what ensures that there's no holes or jumps or anything like that. So we will do one example using the definition, and then we'll sort of expand it to the more general form. So if we wanted to use the definition to show that 3x squared is continuous at 1, right? That's this function down here. The way we would do this is first we would show what the functional value is. So f of 1 is 3 times 1 squared, which is 3, okay? And then we'd look at the limit as x approaches 1 from the right of 3x squared. We would look at the limit as x approaches 1 from the left of 3x squared. And so if we were to plug in some values close to 1, we would use things like, so our x values and our 3x squared values. So from the left, we would use things like 0.9, 0.99, 0.999. That's how we get close to 1 from the left. And if we were to do this from the right, we would pick things slightly bigger than 1. So 1.1, 1.01, 1.001, okay? And so I want to show you one calculator trick real quick. Hold on, let me grab my calculator. for when you're plugging in a lot of values. So you don't have to use this trick, but I find it helpful. If you put your function, if you go to y equals on your graphing calculator and you type in your function, so here I have 3x squared, okay? You can then use the table function to sort of plug a lot of things into it. So here your table is like back here in blue. So I have to do second table, okay? And then you can enter the values you're interested in. So I would do 0.9, enter, 0.99, enter, 0.999, enter, 1.1, enter, 1.01, enter, 1.001, enter, right? And so it helps me see the values. The last one you can ignore. That's not, let's see, 1.0001. So it lets you plug a lot of values into the same function. And it's just sort of, for me, a quicker way to plug things in. And then I can see, like, for the 0.9s, right, that's approaching 3. So I have 2.43, 2.94, 2.99, right? And then from the other side, for my 1.1, I have 3.63, 3.06, 3.006, right? So those are both approaching 3. So if you are comfortable using your calculator, that is a slightly faster way to plug things in instead of doing it one at a time. Okay, if you have a Casio, there is a similar function, but I don't know the functionality of that. So either way, these are both approaching 3. And since these are the same and they are the same as the functional value, that means that we are continuous, okay? So that is the mathematical definition. However, as I mentioned, we are going to do this a little more informally, and we are going to link back to what we know about domain and range from chapter 1 to link this up to continuity. So what does that look like? Okay, so it turns out that there's a lot of different types of functions that are continuous wherever they are defined. Okay, so what does that mean? That means wherever their domain exists. And so that's one of the ways math works, right? We look for patterns, and then once we find those patterns, we're able to come up with ideas and formulas. And so that's what's happening here, right? If you evaluate the continuity of a polynomial, you'll find that it's continuous everywhere because the domain for a polynomial is all real values, right? So polynomials are your x squared, your x cubed, things like that. So the functions that are continuous wherever they are defined are polynomials, exponentials, sine and cosine, and any way that you compose those types of things. So like rational functions, right? So if you have one function over another one, that's 2 polynomials. So what we want to be able to do is look at a function and think about what the domain is in order to tell us where a function may or may not be continuous. So I'm going to write this just a little bit bigger. So we have f of x equals 2 divided by x minus 4. What I want you to do is I want you to take 1 minute and jot down the domain of this function. So the question is, what can we plug into this and not be worried about it? What values? So think about that for a minute and jot something down. Okay, so hopefully when you saw this function, you were thinking, I'm a little bit worried about plugging in 4, right? So 4 is the number we're worried about because we don't want to divide by 0. So here, this function has a domain, so we'll start with that, that x, we'll say, goes from negative infinity to 4 and 4 to positive infinity, right? We can write it like that. You could just say x does not equal 4. That's another way we can write it, okay? So that tells me that I'm continuous everywhere but 4 because I am defined everywhere but 4. So if we can determine the domain of a function, we can then figure out where it's continuous. It's the same place, okay? As long as the functions fall into these categories, and this is a rational function, which is a polynomial over a polynomial. So we can link up domain, I would say, in 90% of the cases where we're trying to figure out continuity. There are a few times where we have piecewise functions like this, where we can't just use that. And that happens because we are using two different functions. So those are like the pictures we looked at before, where there's one function to the left and one to the right. And so we're trying to determine, does the value change, right? Does the function jump? Does the function have a break, right? And so if we look at something like this next example, x squared minus 4 for x less than 0, and x minus 4 for x greater than 0. Individually, those functions are continuous everywhere, right? The domain for x squared minus 4 and the domain for x minus 4 are both all real numbers. There's no problems there. But we have to be concerned about where we change functions. And so that happens at x equals 0, right? So there's sort of two ways we can deal with this. We could use the limit definition and do the limit from the left and the right, but we don't even have to do that. We can just evaluate if it jumps by plugging in 0 into both functions, since there's no concern about zeros for either of those functions. So if we were to plug 0 into the top function, right, we would have 0 squared minus 4, which is negative 4. If we plug 0 into the bottom function, 0 minus 4 is negative 4. Those are the same. And again, I picked 0 because that's where the function changes on the left and the right, but the functional value is the same. So that means that we are going to be continuous everywhere, right? We thought that there might be a jump, but there wasn't, because the functional value stayed the same. Okay. So finally, let's consider this function here. And I want you to think about this. I'm going to have you try to figure out and draw this out and see if you can figure out the continuity here. But the idea is that we have this pay by the hour parking garage. So any fraction of the first hour is $8, right? So you pull in, you have to pay $8 for the first hour. And it doesn't matter if you say 10 minutes or 50 minutes or 30 minutes, it's $8. It's a flat fee for the entire first hour. This is how parking garages tend to work. At the next hour, so as soon as you go over 1 hour, right, you have to pay another $8. So it jumps up to $16 to be there for any part of that second hour. So from 61 minutes to 120 minutes. From there, it would jump up to $24. So another $8 for the third hour, right? So what I want you to do is I want you to think about this model, okay, and think about what the continuity is going to look like. So I encourage you to try to graph what you think this situation is going to look like, so that you can think about and see where we might have any continuity issues. Okay, so I'm going to give you about 2-3 minutes. Try to draw out this scenario. Feel free to check in with someone next to you, and then we'll go over it together. All right, take about 30 more seconds to finish up whatever part you're working on. So when we have a word problem and we're trying to think about the continuity, we need to make sure we understand which variables are which. So here, the time is our independent variable. So if we were thinking about graphing it, we put those hours across the bottom, and the cost is our dependent variable. So that's what's going to be up here. So for the first hour, so whether it's 30 minutes, 45 minutes, it's all $8. So it's the same, right? Until we get to the 1 hour mark. At the 1 hour mark, if we leave right at 1 hour, we're good. But anytime above 1 hour, as soon as we get a tiny, tiny bit past an hour, so 1 hour and 1 minute, we jump up to the $16 mark. And the $16 mark is going to be true for any amount of time we are there between 1 and 2 hours, right? Including this 2 hour mark. If we leave right at 2 hours, we're good. But if we stay for even 1 minute more, we jump up to the 3 hour mark, right? So anything slightly to the right of 2, we jump up, right? So we end up with this function that's called a step function where we're jumping up. And so what we get from this is that if we are between hours, we're good, we're continuous. However, right at these changes, the same thing would be true going from 3 to 4 hours, right at the minute we change, so at the 1 hour mark, the 2 hour mark, the 3 hour mark, the 4 hour mark, we are not going to be continuous because that's where we jump. Okay, but we are continuous in between. It's just at these points, 1 hour mark, 2 hour mark, 3 hour mark, where we have the jump. And so whenever we have a jump or, a hole, things like that, that's where we're not continuous. So if you have a word problem, I strongly encourage you to think about drawing it out. It often helps you identify the places where you're going to have what's called these discontinuities to help you figure out where a function is and is not continuous. Okay. All right, so that's our last problem for today. So I'm going to let you guys go. If you have any questions about this material or the midterm 1 stuff, or just questions in general, feel free to stop by the computer on your way out or shoot me an email. Otherwise, have a good rest of your day.